Looking at section 11.3, limits and continuity, we're going to determine whether a function is continuous at a number and determine for what numbers a function is discontinuous. So in the beginning of this section in your textbook, they have this image to kind of introduce the limits and continuity. So it says in figure 11.12, shows three graphs that cannot be drawn without lifting a pencil from the paper. In each case, there appears to be an interruption of the graphs of f at x is equal to a. So the first graph, as you're kind of reading the graph from left to right, it's coming down on the curve, and then there's a hole in the graph, and then it continues. You would not be able to start from the left side to the right side without having to lift your pencil. The next graph in the middle there, we start with a piecewise function. So as we're going from left to right, it's coming up until it gets to this point here where it has that open circle. And then you have to lift up your pencil to go to the next point to get started on the rest of the graph. And then the third one, very similar to the first, where it still has that hole in the graph. So as you're going from left to right, you go until you reach that hole. You have to pick up your pencil to put this other point, and then you have to pick it up again and then continue on that parabola. So what happens with continuity, the main thing is if you can start from left to right and continue your graph without having to pick up your pencil point, that's kind of showing what continuity is. It's a continuous graph. You have a starting point and a stopping point and no interruption in between. So what happens with our definition of a function, continuous at a number? There are going to be three things we have to look for. So it says a function f is continuous at a when three conditions are satisfied. Number one, f is defined at a, that is, a is in the domain of f, so that f of a is a real number. Number two, the limit as x approaches a of f of x exists. And number three, the limit as x approaches a of f of x is equal to the value of the function at a. So just like what we've done in the previous section or two is when we evaluate these limits, we have to evaluate it where it's equal to the same value. So let's take a look. Determining whether a function is continuous at a number. So it says determine whether the following function is continuous at 1. So if we have f of x is equal to an x minus 2 divided by an x squared minus 4, we would want to check our conditions. So it says according to the definition, three conditions must be satisfied to have continuity at a. So condition number 1 is that f is defined at a. That means if I plug in the number 1, I'm going to end up with some sort of answer. I'm not going to have an undefined answer like a divide by 0. So if I take 1 and I plug it into my function, we're going to take a 1 minus 2 and then divide by a 1 squared minus 4. All I did is I plugged in for my x values. I plugged that number 1 in. So if I simplify that down, 1 minus 2 on the top is a negative 1, and 1 squared is 1, take away 4 is a negative 3, and a negative 1 divided by a negative 3 is a positive 1/3. I don't have an undefined answer, which means that this is defined. Step number 1, it has to be defined at a. Check. Condition number 2. Condition number 2 tells us that the limit as x approaches a of f of x exists. So now we're going to double check the limit of the top and the limit of the bottom and see if that works. Well, as x is approaching 1, if I were to take a 1 minus 2 and compare that to a 1 squared minus 4, we're going to end up with the same exact value. We're still going to end up with that positive 1/3, just like what we did for checking condition number 1. So in this case, this exists, right? It's not a does not exist. The limit exists when I evaluate it at that 1. Condition number 3. It wants to know that the limit as x approaches a of f of x is equal to f of a. Did we end up with the same answer? When we checked condition number 2, we checked the limit of that. We ended up with a positive 1/3. When we checked condition number 1, the value of the function at 1, we ended up with a 1/3. And so it says because the three conditions are satisfied, meaning we got yeses on all of them, we have an answer for all of them, we conclude that f is continuous at 1. Now let's try another number. The next one, same function, but this time we're going to check to see is it continuous at 2. So number 1 condition. F is defined at a. So that means we need to take, if we were to plug in a 2 for x. If you think about it, if I take a 2 minus 2 on the top and a 2 squared minus 4, first thing I would notice is that I would end up with a 0 divided by 0, and if we define by 0, something funky is going to happen. This is going to end up having some sort of problem at this number 2. So this one tells us to factor the denominator of the function in the equation, kind of to see if there's a way that we can simplify this down a little bit more. Well, our x minus 2 is just going to stay the same on the top. But if I have an x squared minus 4, that's that special case x plus 2 and x minus 2. And typically we would look to see, if we're looking for the domain of our function, what are the limitations of the denominator? Well, if I have an x plus 2 as a factor, that means that x cannot be equal to negative 2. And if x minus 2 is a factor, that means that x cannot equal positive 2. Those are our limitations to our domain. Well, if we're checking for continuity at 2, we just said that x cannot be equal to 2. That means that f is not, that should be an is, not an in, is not defined at 2. Therefore, f, the function, is not continuous at 2. And so we could also call this a discontinuous function. So f is discontinuous at 2. So the next part, determining where functions are discontinuous. It says if f is a polynomial function, the limit as x approaches a of f of x is equal to f of a for any number a. A polynomial function is continuous at every number. Many functions are continuous at every number in their domain. Rational, exponential, logarithmic, sine, cosine, tangent, cotangent, secant, and cosecant functions are continuous at every number in their respective domains. And now if you remember back to like the trig unit, we had to look at their respective domains, meaning we know that some of our functions, like our tangent function and our cotangent functions, they're going to end up at some point not being continuous, like a sine and a cosine type graph, because they give us a slightly different graph. But if we limit that to the respective domains, we can make it a continuous graph if we're only looking at a section of that graph. So let's look at an example. This one says determining where a piecewise function is discontinuous. So it wants us to determine for which numbers x, if any, the following function is discontinuous. So we have a piecewise function. We have 3 pieces. F of x is equal to, the first one, 2x. If x is less than or equal to 0, it's going to be an x squared plus 1 if 0 is less than x, which is less than or equal to 2. And the third piece is a 7 minus x if x is greater than 2. So it says first we determine whether each of the 3 pieces of f is continuous. So if we look at that first piece, the first piece here tells us that we have a 2x. 2x tells us that this is a linear function. Is there any limitation to a linear function? This is going to end up being continuous at that, continuous for that piece of our function, right? Linear. There's no limitation to that. The second piece, we have a second power, which tells us that is quadratic. Now, if you think about your quadratic functions, our parabolas, our U-shaped graphs, is there any limitation to our domain of that? That's also going to be continuous. And then the third piece is back to another linear function. Any limitation with a linear function? No limitation. So we know that that's going to be continuous at every number for x. So again, looking at these pieces, it says we have, kind of skipping down halfway through that, we have determined that each of the 3 pieces of the functions are continuous at x. We now investigate continuity at x is equal to 0 and x is equal to 2. Why are we going to look at those 2 pieces? Because we have a change from a 0 to a 0, and we have a change from this 2 and the 2. So we have 2 changes that are occurring in our graph. Something's changing at 0 and something is changing at 2. And we want to know, can I go from left to right on my graph without having to pick up my pencil? That's kind of the idea between continuity. So we're going to evaluate those 2 pieces, x is equal to 0 and x is equal to 2. And so it says we begin by investigating continuity at 0, the first one. So the value of the function at 0, where is 0 included? I'm going to erase all these little arrows up here. Where is 0 included in our graph? Well, x is equal to 0 in the first piece, so we're going to see what happens when we evaluate 2 times 0. Well, 2 times 0 gives us 0. So because f of 0 gives us a real number 0, so we're going to say is a real number, we can say that f of 0 is defined. There's no problem with this. All right, we got a whole number. We got a 0. It's a real number. Let's see what happens when we look at the limit of it. So the limit as x approaches 0 from the left, right? That's what our little negative sign at the end there. So the limit as x approaches 0 from the left means that we have to find the left side of 0. So if I'm looking for the left side of 0, I'm looking at the less than part of 0, which means that I would evaluate the limit of that 2x, which means I'm looking at that 2 times 0, which is equal to 0. And then if I go and I evaluate it from the right, the positive, that means I'm going to look at from 0, I now need this piece. So I'm going to evaluate that x squared plus 1, which means I'm going to have a 0 squared plus 1, which gives me 1. Well, now if we take a look at the two values we get, do we get the same number? So the left hand and the right hand limits are not equal. What does that mean? It means that the limit does not exist. That means that the function is discontinuous at 0. Or I guess that x is equal to 0 would be a better way to put that. X is equal to 0. Now, all they wanted us to do was determine for what numbers x, if any, the following function is discontinuous. I already found that it's discontinuous, which means I don't need to double check my second value here. If it was continuous at 0, I'd have to follow that same process to double check that other jump in my graph.